This is the introduction slides for paper 3008-47 in CUP 2023. This paper's motivation is targeting at the domain shift problem in zero-shot learning. Conventional zero-shot learning suffers from the domain shift that there is a gap between the real and the modeled distribution of those unseen data. However, transductive zero-shot learning assumes that we could access the unseen data in the training stage to alleviate the problem, but the problem is still existing for those resemble classes like the seals and the vortices. In this work, we propose a novel bi-directional approach to address the domain shift problem in zero-shot learning. Specifically, we use an extra distribution module to get the generation of visual features. Meanwhile, we discuss the importance of marginal distribution for modeling the conditional generation. That means by using a real class prior distribution, the convergence of alignment could be easily landed. To solve the problem, we additional propose a clustering prior estimation approach. First, we start with the generative baseline of VAEGAN. It uses a conditional VAE and a conditional GAN to train the generator using the paired scene data. The generator here plays the role of knowledge transferring module. For the unseen data, since we only know the marginal distribution of the unseen data and the class priors, LVAEGAN uses an unconditional Wasserstein GAN to leak the unseen information to the generator. However, LVAEGAN suffers from the weak constraint alignment problem. That means it cannot distinguish the resemble classes using only the unconditional distribution matching, and it cannot generate realistic visual features for those hard classes. It also uses the strong assumption that the class prior is given, and it neglects the hard cases that the class prior is unknown. I'll by VAEGAN first to address the aforementioned problem. Our method first adversarially train the regressor that maps the visual features to the attribute space. It links the regressor with both the marginal distribution of visual features and the attribute factors. Attribute factors, thus we call it as the transductive regressor. The training of a generator is mostly consistent with the training of a VAEGAN, but we additionally introduce the transductive regressor here as a distribution module to get the generation of the unseen data. That means we enforce the generated unseen feature could be mapped back to its corresponding attribute factor. This introduced the extra distribution for the forward distribution alignment. So we want to discuss the importance of class prior in the distribution alignment process. Using the generalized label shift theory in domain adaptation, we could find the distribution gap, the conditional distribution gap, distance gap, is upbounded by the equation here, and given the non-class prior, the third term of the bound will collapse to a simple JSON distance between the marginal distribution of the generator and the real the real one. And this is exactly the optimizing problem the unconditional GAN is dealing with. So given the non-class prior, the convergence could be easily achieved using a simple unconditional Wilson GAN. But to make the model work in the hard non-class prior cases, we propose a cluster prior estimation approach. Specifically, we only use the marginal distribution of unseen features. So we utilize the clustering property of the visual features as the prior of the unseen class distribution. And we iteratively update the sampling prior using the k-means label at the end of each epoch until the chaining is converging. In experiment, we evaluate our method in 4 benchmark data sets in both zero-shot learning and the generalized zero-shot learning. And in most of metrics, we arrive at a new state-of-art performance. We also marked those methods that uses the non-class prior with the notation dagger. We also evaluate the importance of the class prior. For first, we showed that if we use a naive unknown, you use a naive uniform prior, the performance dropped to a great extent. By using our cluster prior estimation module, we could approximate the true marginal distribution well, and thus we could achieve a good accuracy. We also evaluate our model in different auxiliary knowledge. We use 3 kinds of knowledge here. The first one is the attribute, and second is the textual embedding, and the third is the proper type averaged from unshot data. We found that by using transductive regression, the result is more robust to the quality of the auxiliary knowledge, which the support number as the support number increases, we think the quality of the knowledge is better